All right, so today is the last piece of material. Now, at the end of chapter 7, we talked about, I called it the king of the hill for all real valued matrices. Okay, and that was the symmetric matrix. We guaranteed that eigenspaces were mutually orthogonal. We guaranteed that the eigenvalues were purely real. Now, is there a complex version of this? Yes, there is. So we need to define something first. All right, let's call matrix A the following. I have A plus BI, C plus DI, E plus FI, and G plus HI. Okay. Any of the A, B, C, D, E, F, G, H can be 0. Any of them can be any real number. We know what the transpose of a matrix is. We know what that is. I want to define something, we call it A star, where this is the conjugate transpose. Now you remember when we sort of redefined dot product, we realized we have to take the conjugate of the second vector. So when you're doing things with matrix multiplication or vectors in general, taking conjugates is actually a very common thing. So what A star would be, it's the conjugate transpose. So the diagonal entries, I would clearly have these, and then the non-diagonal entries, to make the transpose, I got to move things. But these guys also are the conjugates. So this would be called the conjugate transpose. You don't do it as two separate steps. You do it at one time. Okay? So mentally transpose and then take the conjugate of each term. Does that make sense? That's a pretty simple thing. So physically doing this is not an issue. Now, we define something, we say A is Hermitian if A equals A star. Hermitian is kind of the complex version of symmetric. A symmetric matrix equals its own transpose. A Hermitian matrix equals its own conjugate transpose. Okay? And you will never just find the transpose of a complex matrix. That doesn't serve any purpose. Okay? So if I have something like this, is this Hermitian?
Yes. No.
Well, if I transpose these guys and then I take the conjugates, this will work, won't it? Now what do you notice right off the bat then? Compared to that one over there, what do you notice?
The diagonals have to be real.
The diagonals have to be real. Oh, so if a diagonal entry equals its own conjugate transpose, the diagonal entry would have to be real because it has to be plus 0i minus 0i. So this would be an example of a Hermitian matrix. Okay, so we're going to look at Hermitian matrices. In the textbook, they're probably the first 80% of the practice problems are just find the conjugate transpose. Is this matrix Hermitian? Just kind of basic arithmetic stuff. It's just not very interesting, and you probably shouldn't spend more than a few minutes on it. Our goal is to actually diagonalize this matrix. Okay? Now, in the real valued, hold on, where's the eraser? Am I not seeing something? Oh dear, I don't even have one of the nasty rags up here. Oh dear. Why don't you guys leave with the eraser again? I blame it on our new puppy because she chews everything up, but she's not here, so I don't think she ate it. Okay. I think I'm going to see it somewhere. Well, all right. With the real matrix, our idea was to do something like this. For symmetric A, we did P transpose AP to get the diagonal matrix where the eigenvalues were in the main diagonal. Now tell me about P and P transpose.
Inverses.
Yes, but even more than that, they are inverses.
P inverse equals P transpose.
Yes, So, we had a name for them.
Oh, there,
What was the word? Orthogonal. Orthogonal matrices. Well, what makes something an orthogonal matrix? I know it's been ancient history. It's because the columns formed an orthonormal basis. My columns of P are the eigenvectors, but they were mutually orthogonal and unit vectors. That was the key. Oh, that's why I had to manipulate this in order to make these into unit vectors, because P will not equal P inverse, okay, in general, but if I do this, then B transpose will equal P inverse, okay? The problem if I don't make them unit vectors is that I may multiply out to a diagonal matrix, but it will be multiples of the identity, not the identity itself. So on the last quiz that you guys just turned in, on the first problem, you had to find P and P transpose. But if I don't make those into unit vectors and I do my P transpose AP, you found that you got a diagonal matrix, but it wasn't the eigenvalues. It was multiples of the eigenvalues. You'll say, why didn't this work? Well, because I didn't make things into unit vectors. So P and P transpose are called orthogonal matrices, and P transpose equals P inverse in this case. Okay, so now let's look at the complex version of this. Now, can I do this for any square matrix? Can I do P transpose AP for any square matrix and get a diagonal?
no.
No, only for
Symmetric.
symmetric. It's special. In general, no. In general, P transpose is not going to equal P inverse. If I just give you some eigenvectors in general, no, they're not going to be mutually orthogonal eigenspaces. But for the symmetric matrix, we proved that they are. So the complex version of this, we're going to define something called the unitary matrix, P. The unitary will be the equivalent of this. Well, in this case, the key was that P transpose equaled P inverse. So over here, what do you think it'll be? Based on what we just did. Not P transpose, but
Star.
P conjugate transpose. Ah. So again, the complex version of this is I'm going to do the conjugate and take the transpose. And that means, once again, that after I find my eigenvectors, I need to make them into unit vectors. I have to have an orthonormal basis. And making a complex vector into a unit vector is not a trivial thing. In fact, it doesn't even have unique looking things. We're going to do a couple of examples where I'm going to show you. Oh, okay. We're going to do stuff where you did everything right. I mean, you check your answer and the answer looks very different from yours. I mean, the vectors do not even look similar, but you're still correct, because depending on how you chose to parameterize and other factors. Okay? Everybody cool with this? Let's actually take a problem from beginning to end. Let's do, let's say matrix A equals 4, 6, 2 minus 2i, 2 plus 2i. All right? All right, first of all, is this Hermitian?
Yes.
Okay? Now, something I still need to show, lest I forget. Let me take a matrix here. Almost forgot to do this because I proved this for the symmetric. The author does a completely different type of proof that's valid but a little bit harder to follow. A, B plus, Ci, B minus Ci, D. This is a Hermitian matrix. I want to find the eigenvalues. I probably should have started with this. Oops, A minus lambda. Okay, nice. I would use my hands, but I have a feeling I'll be completely coated by the end of the class if I do that. Okay. So when I do this, I'm going to get AD minus A lambda minus D lambda, lambda squared. What is B plus Ci times B minus Ci?
B squared plus C squared.
B squared plus C squared, and I'm subtracting that, aren't I? Okay, we all agree with that? So this is equal to what? This is equal to lambda squared minus a plus b times lambda plus AD minus b squared minus c squared. We want to write it that way. Yeah. Now, all of those obviously are real. I didn't even hear that. Good catch. So, like we did before, let's use our quadratic formula to figure out, what the eigenvalues look like. So I would get lambda equals a plus d plus or minus, and on the bottom that's a 2, so it'd be the square root of the square of a plus d minus, as always, 4 times that other thing. Okay, does that look about right? Well, let's see. I just want to look at the discriminant now. I know those are my eigenvalues. What I'd like to know is, are they real? Are they complex? Are they both? Okay, so let's take the a plus d squared minus 4 times AD minus b squared minus c squared. And let's expand this. So that'd be a squared plus 2AD plus d squared minus 4AD plus 4b squared plus 4c squared. But I can combine these two. So that's a squared minus 2AD plus b squared. And then I have these guys left, plus 4b squared plus 4c squared, okay? But isn't this just a minus b quantity squared? And what do you notice? I have a sum of squares.
You should take out the 4.
Oh, thank you.
So I think it's a plus d squared.
Did I lose something? A minus d, thank you.
Yeah.
Oh, I see, I wrote b over here. It's the new math, there we go. Could this ever be 0? Yeah, if b and c are both 0 and a equals d. If b and c are 0 and a equals d, then I'm starting off with a real diagonal matrix to begin with, aren't I? Boy, that's kind of boring. And then we already know the eigenvalues would just be those entries. So what do we got? We've got the eigenvalues of a Hermitian matrix are real. Ooh. Now, eigenvectors are not going to be real, but the eigenvalues at least are. Working with complex eigenvalues can be nasty. That can be really, really difficult. But in reality, you're never going to, because you're only going to look at problems that have real eigenvalues. So, this is Hermitian. Therefore, I'm expecting my eigenvalues to be real. I want to walk you all the way through the problem from beginning to end. We're going to find the eigenvalues, we're going to find the eigenvectors, we're going to find the unitary matrices, P and P star, and then see if we can diagonalize. The process is not trivial, and I only need you to understand it's for a 2 by 2. We can do a 3 by 3, but it will take a lot longer. Okay, I think you're okay with that. And what does this give us? 24 minus 10 lambda plus lambda squared. What's 2 plus 2i times 2 minus 2i? Technically it would be 2 squared plus 2 squared. So that'd be 8. So minus 8 because I'm subtracting. So lambda squared minus 10 lambda plus 16. That would be lambda minus 2, lambda minus 8. What do you know? Real eigenvalues. Beautiful. So lambda 1 will be 2, lambda 2 will be 8. Okay? So let's find our eigenvectors. So starting with lambda 1 equals 2. So A minus 2 times the identity matrix. Now I have to remind people what we're doing. We are solving a system of equations. There's no such thing as a parameterization of something that's not an equation. You only parameterize equations. You don't parameterize algebraic statements. You don't parameterize a vector. You don't parameterize a matrix. You parameterize this equation in the end. So when I'm doing this, the easiest way is to augment it with zeros. So I'd have 2, 2 minus 2i, 2 plus 2i, 4, and now I'm augmenting it. I'm seeing a lot of people just take the matrix and then they parameterize it. Well, there's no equation. A matrix isn't an equation, and a matrix cannot be parameterized. You are solving this. You don't solve a matrix. Again, there's no equation there. Well, I'm just saving time. No, you're actually writing something that doesn't make any sense. It'd be kind of like me putting down x. That's it. No equation, just x. Well, x doesn't have a value. It's just a variable. I can't now make it equal something because there was never an equation to begin with. So when I do this, is the second row actually a multiple of the first row? I don't know if that's entirely obvious. So maybe one thing we might want to do, well, I could multiply the first row by a half. That might actually be a good idea, because then parameterization is probably easier also. So if I multiply the first row by a half, what would I multiply row 1 by and then add it? It'd be the negative of 2 plus 2i, agree? So I'm going to write it out. So negative 2 plus 2i row 1's added to row 2. Well, I know that's going to be a 0. So let's do 1 minus I, technically times negative 2 minus 2i. And then I'm going to add that to 4. Is that what I just said I'm going to do? The negative of 2 plus 2i, excuse me. Oh, I'm sorry, I got the wrong. No, I got the right, yeah. The negative of this, multiplied by that, added to 4. That just doesn't look friendly, does it? It looks icky. Well, let's do it. So I have negative 2 minus 2i plus 2i plus 2i squared. Plus 2i squared would be minus 2. Oh, it does equal 0. That's the one thing about doing this process with a complex matrix. It isn't always obvious. Yes, those two rows are in fact multiples of each other. They had to be if I did it right. But are they obvious when you look at them? I don't think it is. Okay, I don't think it's obvious. But everything I said was true and correct. Okay? So far so good? Now we want to parameterize this. I didn't have to. I could have multiplied by 1 plus I and then do the negative of 1 plus I. But I think for parameterization, having ones might make it a little bit easier. So the question is, what should I call my thing? I mean, do I say let x1 be t? Do I say let x2 be t? Do I say let x1 be something else?
I think you say let x2 be t so you don't have to divide a complex number.
That might be more logical. Yeah, it'll be easier if I, remember the rule of thumb is if one of them's a 1 and the other one's not, always go for not. Does that sound familiar? That just makes it easier in general. So if I said, well, let's let x2 be t, then what would x1 be? It'd be the negative of 1 minus I t. Now, a lot of folks would say, well, you know, I want to make x2 just be negative t then. Does that seem like that might make it a little bit easier? A little less algebra taking place. I think that might be a more logical one. And I'm going to show you there are several good choices. So how about we make that negative t, then this is positive 1 minus I times t. So that any vector of the form 1 minus I t comma negative t, which is t times 1 minus I negative 1. So we will choose our first eigenvector to be 1 minus I negative 1. Is this the only choice I could have made? No. Now, what is 1 minus I times 1 plus I? 2. So I'm going to show you another really good choice. What if I said, and by the way, this is probably more likely the one you'll even see in the textbook. What if I'd said this? Let x1 be 2, or even better, negative 2 for the same reason. Then x2 would be 1 plus I times t. Because 1 plus I times 1 minus I is 2. Does that make sense? This is a perfectly good parameterization. If we had done this parameterization, then our vector would have looked like -2, 1 plus I. And I'm claiming that these vectors right now are multiples of each other. They're exact multiples of each other. Take the negative of 1 plus I and multiply it by that one, and you'll get this one. There are other parameterizations. We could go with +1 and then -1 plus I. We could go with +2 and then -1 minus I. So right now I've given you 4 equally correct parameterizations. I'm probably a bigger fan of the first one because I'm sticking with all ones. Although I've seen the textbooks are just as likely to have this one. Because of the next vector, really, is what it comes down to. Now, the reason I'm showing you this is these two vectors do not have the same length. So the root that shows up in my matrix will look very, very different. My P and my P star will not even look like they came from the same problem when I use one versus the other. And that's my point, is that you can do everything right, your answer doesn't look similar, and you're still right. You just chose a different path. Normally a parameterization, it's really easy to see, you know, oh, I just picked a multiple of that. But your multiples now are complex multiples. They're not scalar, simple scalar multiples. See, we think of a scalar multiple as being a real scalar. But these are complex scalars. All right, let's now do the second one. So, oops, lambda equal, what was my second eigenvalue? 8. So a minus 8 times the identity augmented with zeros. So -4, 2 minus 2i, 2 plus 2i, and minus 2. Whew. This really doesn't look as fun, does it? Any ideas? I don't like a pivot of -4 in this situation.
Switch rows.
Doing a row switch would make perfect sense. So let's do a row switch. Should we multiply the first row by a half like we did before? And again, that might make it a little bit easier. It's whatever works. I don't need to multiply the second row. That's not going to save me any time in that sense. If I multiply row 1 by 1 minus I, that becomes a 2, and that becomes a -1 minus 2i. So if I said 2 times 1 minus I times row 1, and I add it to row 2. So 1 minus I times 1 plus I, we just said that equals 2. So if I do 2 times that, that's 4. And clearly then I'm going to have a 0 there. Now, I'm going to go 2 times 1 minus I. That means it's going to be -2 plus 2i. And now I'm going to add it to 2 minus 2i, and that's obviously 0. That one worked out pretty well. So now we're going to parameterize this guy. So, I will choose, well, now here's how you make the choice. Most people will do the following. I have the complex piece as the first component and the purely real as the second component. I would kind of like my second eigenvector to follow suit. It just actually makes it easier to work with. But if I had gone with the second one, just the opposite would be true. So in this case here, if I say, well, the obvious choice is to let x1 be t. I just think that's the obvious one in this case. Let x1 be t, because then x2 is simply 1 plus I times t, isn't it? That one, to me, that's really obvious. Then I'd say any vector of the form t comma 1 plus I times t, which is t times 1 1 plus I. So I will choose my second eigenvector to be 1 comma 1 plus I. Certainly the easiest one to work with. And it would have been absolutely correct for you to do this one. It's just that in the formation of things, sometimes it can get a little bit ickier. So what a lot of people do, and particularly authors of textbooks, they'll put the real in the same position and put the complex in the same position. It does not matter. It's not a rule. It's more out of convenience. So I think there's no question that this is the easiest version of this vector, and I think this is the easiest version of these vectors, but this is backward. So had I done the thing I did before, I said, well, what if I go the other way? Oh, so what if over here I say, let's call x2. How about if I call x2 2t, then x1 would simply be 1 minus I times t. Then 1 minus I times 1 plus I is positive 2, minus 2. Aha! So my other eigenvector choice here would have been 1 minus I comma 2. It's a perfect choice.
If you can see that that's a multiple of the first one, could you go straight from that first parameterization and then say choose x2 equals 1 minus I comma 2?
Well, I'm sorry, are you talking about?
Like if you, okay, so earlier we chose
You're never
that
going to
one.
do both of these.
Right, but
I'm just saying these are two versions of the same answer.
But could you just go from one to the other with multiplication?
However, it doesn't matter how you pronounce it, as long as you do it correctly. Yeah. Now, here's my point. We have two completely different versions of the first, we have two completely different versions of the second, and it doesn't matter which one you choose, but the most common thing you'll see, again, is the real and the complex in the same position within the vector. It actually makes certain things a little bit easier. Now, I want to do a dot product. Let's deal just with the first vectors, just to see. I want to do x1 dotted with x2. When I do that, I have 1 minus I times 1 plus negative 1 times what? 1 minus I, because it has to be the conjugate of the second one. And what do you get? One of them minus one of them, isn't that? Is that a good thing? Yes, that means they're mutually orthogonal. Oh, just like with the orthogonal matrices, right? The eigenvectors formed a mutually orthogonal set of vectors. I'm going to get the same thing here with the unitary matrix. I'm going to get mutually orthogonal. Would it have mattered which dot products I did? No. Does it matter which vector I use from each side? No. Then why am I showing you two versions? Because let's find the length of these two vectors now. What is the length of my x1? How do we do that again? 1 minus I times 1 plus I plus negative 1 squared. That's root 3. Over here, what's the magnitude of my x2? 1 squared plus 1 plus I times 1 minus I, and again, that's also root 3. So how in the world does this get wonky at all? Let's find the length of that x1. This was my check. You should always be doing the check. Okay, this version of x1, the magnitude is the square of negative 2 plus 1 plus I times 1 minus I. So that's 1 plus 1 is 2 plus 4 is root. Oh. Wait a minute. When I parameterize this way, I got a vector of length root 3. When I parameterize that way, I got a vector of length root 6. What's the magnitude of this guy? I think it's obvious. It's also root 6, isn't it? Does it matter which ones you choose? Nope. But what do you I don't know. You can have root 3s, you can have root 6s, it doesn't matter which way you go. Some might argue, you know what, I don't care where the real and the imaginary parts are. I think I'd like them all to be the same root in the denominator. What about that? Might that make it easy to multiply and check later? Yeah, maybe. The reason I'm showing you multiple ways mainly was to get to this point in the problem. To show you the same problem can have two different magnitudes just because of your parameterization. I have to find a p and a p star. I'm going to have roots in my denominators of every term. I think life would be a little easier if all of your roots were the same. They don't have to be. It will still work just fine. But it might be easier if they were all the same. Okay? So with that said, let's see. I'll do it over here. I'll put it in black ink. What is my first unit vector going to be then? I'm going to write it this way. 1 over root 3 minus 1 over root 3, comma, negative 1 over root, I, comma, negative 1 over root 3. What is my second? Well, if you decide you want to stick with the root 3s, then you definitely want this one. So 1 over root 3, and then okay. You with me on that? I need to erase some more stuff. I think I'm going to erase this stuff here. So now, I'm going to write down my matrix P. I'm not going to alter these guys. The only time you alter the vector is when you're actually physically doing a dot product. You take the conjugate of the second one in the actual dot product itself. I don't call U2 something else, but if I do U1 dotted with U2, I do this value times this value, and then this value times the conjugate of this value. That's what I do, and then I should get the number 0 when I'm all done. So now when I'm writing my matrix P, okay, 1 over root 3 minus 1 over root 3i, negative 1 over root 3, now I'll write my u, 1 over root 3, 1 over root 3 plus 1 over root 3i. Now, I called my first eigenvalue 2 and I called my second one 8. Do you have to stick with that order, or could you have done it in reverse order? And if you did it in reverse order, what would your P matrix look like? These columns would be switched, wouldn't they? Oh my goodness. Nothing about this answer is unique, is it? Now, what is P star? Well, conjugate transpose, I don't have to do anything with these guys other than transpose them. Oy vey. Okay, I'd like to multiply these out. This is the only reason that I stuck with the same roots, because I think multiplying it out, if you have root 3s and root 6s and you got root 18s that they may or may not be so clean. But I got root 3s times root 3s, those just give me 3s. I think that might be easier. So let's do P star, shall we? So I'm going to go this way. These are conjugates. Beautiful. So I got 1/3 plus 1/3. That's 2/3. Times a third. Or, excuse me, plus a third. Now let's do this. I'm going to have negative a third plus a third I. I'm sorry. Negative 1/3 plus 1/3 I. Plus a third minus 1/3 I. Does that equal 0?
Yeah.
That's a good thing. Right, I don't want to do all that in my head. So negative a third minus a third I, plus a third plus a third I. Pretty clear that's 0. And then finally, So I've got plus a third, plus a third, plus a third. Crowd goes wild. We did it right. That's my check. That's not the answer. That's my check. I'm pretty sure I did all the pieces of the puzzle correctly as I went, but my check was the P times P star actually gave me the identity. So the answer to the question was we wanted to diagonalize this. So now I can say P star A P in that order is exactly what matrix? 2, 0, 0, 8. Do I physically need to perform this multiplication at this point?
No.
No, because I actually know everything's correct. Does that make sense? And I think you'd rather not be multiplying this at this point. It just takes too long. But I would still multiply. And the dot product, and here's the reason you still got to multiply. There are conjugates along the way. Is it possible I messed one of them up? Maybe I didn't take the conjugate when I should have, or I did when I shouldn't have. Is that possible? Especially since this is unexplored territory. Yeah, I think that's exactly the kind of thing that could happen. So by me doing a quick check, now, I could have used this vector. But when I did the multiplications, I'm going to have root 6's in the denominator in some cases. And I think that just makes the algebra a little bit trickier. Now, if all of them had root 6's in the denominator, then there's no issues. It's I don't want half of them with root 3's and half of them with root 6's. And that really should dictate how you choose. Okay? I don't want anybody to do this twice like I did. I was just demonstrating something to you. So you did everything right, and you checked in the back of the book, and their P matrix had no root 3's anywhere. They had root 6's all over the place. And so, of course, you did it wrong. Well, no, you did it, and it checked. You had to be right. But now you understand that depending on the parameterization, it'd be very easy to get a completely different looking answer that's still correct, because my answer is still a multiple. Now, the one thing I did not do, which I usually always do, I was kind of working fast, we didn't check, did we? So I'm going to go back and do the check, because the check isn't quite as trivial as it usually is because of the complex nature of things. But which one? I'm going to check it in this form before I make a unit vector. It's easier to check. So let's do that check. 1 minus I, 1. Okay. We already know this answer is completely correct. So I'm going to erase this stuff.
That should be -1.
Oh, thank you. Thank you. And this is why we check, right? All right, so when I do this, I'm going to have 4 minus 4i minus 2 plus 2i. And then here I'm going to have 1 minus I. Oh, boy, that's going to be icky. Except that this is, think of this as 2 times 1 plus I. I'm going to be lazy. Because what's 1 minus I times 1 plus I?
2.
This is 2, so this will be 4. Aha. And then minus 6. What do I have on top?
2
I have
minus 2.
On the bottom I have negative 2. And is that in fact 2 times 1 minus I, negative 1? Like I just said, this check is not quite as trivial as they usually are. Because I have nothing but complex numbers. So everything you do, you have to slow it down a bit. Okay? The algebra is going to be the same things in the same order, but not with real numbers necessarily. So everything I just did is exactly how we always do it. It's just that my answer was a little bit trickier. I had to multiply conjugates. That's why we reviewed a little bit last day, to remind ourselves of the algebra required. Stephen made a good point about when I'm doing this, if I make the wrong, maybe not the wrong choice, just if I call x2 t, then I'm going to be dividing by 1 plus I. There's nothing wrong with that, but that means now I got to multiply top and bottom by the conjugate. I got to do all of that extra stuff. That's correct, but it's a lot of extra stuff. Do you agree? So that's why I said, well, since 1 minus I already gives me 2, calling this 2t is a lot simpler, because then I don't have any fractions over here. So that's where you can be a little bit clever when you're doing this. But there's no short, sweet process. We just did the smallest problem that you'll see. They only get bigger than this. We just did the smallest problem. This took a little work, didn't it? So what we've done is diagonalized a Hermitian matrix by using the unitary matrices, which are the complex analogy to the orthogonal matrices. okay? If you're a mathematician and you go on to study math, you will work with complex matrices and you'll be able to master certain things. That doesn't mean that that's the only thing you do in math. Statistics. I've taken a boatload of upper division and graduate stats courses. There's a lot of matrix algebra and statistics, particularly analysis of variance, ANOVA. Everything is about variance, and everything's a matrix. And we deal with a lot of stuff, but we only deal with real-valued matrices. So the symmetric matrix is the king of the hill in the stats world because it shows up often. Again, I go back to my Olympic example. The Olympic data, a large symmetric matrix if I set it up. Now in statistics, the eigenvectors, they call them principal components. So if you're ever doing any reading in stats and you come across the term principal component, it's an eigenvector. And in fact, they don't even call the eigenvalues eigenvalues. I think they call them something else, which is a little confusing. It's the same stuff, but often done in a very, very large scale. There's really no reason to do that problem small scale because of what you're actually doing and measuring. But in statistics, this stuff is really, really important, really powerful, and you're only dealing with real valued matrices. So complex matrices are more for the mathematicians. I can't tell you where this shows up in the physics world. I don't know if it's complex in the physics world. I know in physics you use real eigenvalues and eigenvectors. I don't know if you do the complex stuff. But here's the thing, is because it's Hermitian, even my eigenvalues are purely real. And the eigenvalues do tell us a lot of information. Okay? In the solving of the differential equations problem now, you just turned in a quiz where you solved a system of differential equations and life was good. What if? What if I had complex eigenvalues? Let's keep this simple. Let's just pretend it's a 2 by 2. Okay? If you made up a 2 by 2 matrix right now, if I had everyone do 10, so then we have about 250 matrices. Exactly half of them are going to have purely complex eigenvalues, even though you used only real values in your matrix. Because you're quadratic, right? The discriminant's going to be negative half the time. Oh my gosh. So the fact that you easily can come up with these complex eigenvalues, how does that work for the differential equation? Well, it makes the differential equation significantly more difficult to solve. I don't want to say it makes it more complex. That's a bad play on words, but it really does. It makes it more complicated. And then what you start seeing are sines and cosines, not just exponential functions, show up in your answers, and it gets kind of wonky. We deal with this heavily next semester, but we gradually work our way into it. We don't just jump in. So by the time we get to the eigenvalue eigenvector problem dealing with complex numbers, which in my class is the second to last lecture of the entire semester, you've been dealing with complex numbers and exponential functions for an entire semester. So the algebra at that point is actually very comfortable. You're not troubled by it. It's like I always tell people, never look ahead in a math book. Right? If you're in Calc 1 and you look ahead and then you see this, you freak out. You're in Calc 3 and you look ahead and you see this. Right? But then when you get there, you go, oh, that's all it was. When you get there, you're going to say, okay, that's not fun, but I know exactly what to do. In the DiffEq class, we do not deal with Hermitian matrices. No, we deal with purely real matrices that have purely complex eigenvalues. And therein makes it a difficult problem because now we know the form of the eigenvectors, right, are e to the something d. But if those lambdas are complex, that's a more difficult problem to deal with. And we deal with that heavily in DiffEq. We don't discuss it in this class because it doesn't come up in our circumstance. When we deal with real value matrices in linear algebra, we pretty much stick with real eigenvalues. Not that we can't have complex, but that's a different animal altogether. Okay, it's a very different type of problem that has a different application. So you'll do that in another class down the road. All right? Any questions? Okay, let's go ahead and stop. We are